Hello everyone. Welcome to this webinar on how to accurately perform 𝗿𝗿 in forested area. Thank you for being here today with us. Today for this webinar, we will have a guest, which is 𝗿𝗿𝗻𝗃𝗃𝗀𝗃 from EDF, and also 𝗿𝗿𝗿𝗀𝗃𝗃𝗀𝗃 from Meteodyn, um, to talk about this webinar. There is a lot of people today, so thank you very much. So let's begin the presentation. I let you with 𝗿𝗿𝗿𝗀𝗃𝗃𝗀𝗃 to begin. So have a nice webinar and see you at the end of the webinar. Bye.
Yeah, thanks Bertrand for this introduction. So hello and welcome to all of you to this webinar. I'm glad to be joined today by 𝗿𝗿𝗻𝗃𝗃𝗀𝗃 from the team of EDF Renewables. And today, so the purpose of this webinar is to share an interesting approach to improve the simulation accuracy in forested areas. Okay, so the project, this research project started when the team of EDF Renewables came to us with some questions. So 𝗿𝗿𝗻, maybe you can explain the question you had for this project?
Yeah, sure. Thanks, Edouard, for the introduction. Hello, everyone. So yeah, as Edouard explained, so as a French developer and operator of a wind farm around the world, we are facing more and more projects in forested areas and using 𝗃𝗃𝗃𝗃𝗃 also in complex terrain and using Meteodyn. So we wanted to investigate a bit more how the model it performs in forested areas, and is it really accurate as we could expect, following the basic guidelines? Is it really good performance? And also we were wondering how can we perform the calibration, and how can we ensure the calibration of each parameters of the forest is well conducted, depending on the forest, the tree height and the forest density, and etc. So that was basically the main question we wanted to cover with this studies.
Thanks, 𝗿𝗿𝗻𝗃𝗃𝗀𝗃𝗀𝗃. So of course for us it was very interesting because we wanted to challenge Meteodyn WT on new sites, and you will see these sites are very interesting because very complex. Well, at least huge forest in the sites. So we proposed in the past a calibration methodology, okay, but of course we wanted to simplify it because you will see we needed to apply some filters, okay, so we wanted to simplify the methodology. And of course we always use the roughness, public roughness databases, and one of the main questions was also, are they accurate enough, of course, to apply simulations in complex area. Okay, so this is the schedule of the presentation. I will start with some basics about the software. Okay, so how works the forest model in the software, and then I will explain the calibration methodology. So then 𝗿𝗿𝗻 will present the results of the project. Okay, and the idea of the webinar is also to focus on two representative sites. Okay, we want to explain the methodology, of course, to give clear guidelines for your studies. Okay, so this is the general wind resource assessment methodology. Okay, we provide with Meteodyn WT. So first we have one step which is called the pre-processing. We need to import data in the software. Okay, so roughness and orography maps, domain types, meteorological data, of course. Then during the first step, we will create the site. Okay, so we define this coordinate system, the elements, so the mass location, wind turbine location. Okay, then we go to the second step. So this is the core of the software. So this is the CFD computation. So for those who don't know the software, okay, so it's in a few clicks you can launch CFD computation. The mesh is automatically generated. Okay, we can define some boundary conditions, and this is here where we can, of course, tune the forest model. Okay, so today we will focus on that step. Okay, is how to improve the forest model accuracy in the CFD computation. And at the end, we have the last step, which is called the synthesis. So this step is used, okay, to transfer the windrows from the mast to every point of the site using the CFD results. So yeah, some basics about the software. So this is the definition of the surface mesh. Okay, so we have a structured and oriented mesh. So it means that we have small rectangles to describe the cells of the mesh. Okay, so one specificity of the software is that we have this automatic refinement at the result points. Okay, so it means that close to the points, so we have the cells with the minimum horizontal resolution, and this is what we define in the software, okay, in the CFD configuration. And then we have this horizontal expansion coefficient between, of course, to increase little by little the size of the cell. Okay, so you have here, for example, 2 masts or 2 wind turbines, and we see that we have very small cells very close to these points. Okay, so we have then the vertical mesh. Of course, everything is created automatically in the software. We have a very similar approach, but now we have the automatic refinement at the ground. So it means that we have very small cells close to the ground, and then we have this vertical expansion coefficient. Okay, and we have the same. We have an increase little by little of the size of these vertical cells. Okay, and it's 4 meters by default in the software. So here goes the forest model. Okay, so inside of the CFD and the Navier-Stokes equations, okay, we can act on the wind flow using this approach. Okay, and we have the activation of the forest model if so with this rule, if the bottom of a cell is lower than, so this value 20 multiplied by the roughness length Z0. So when I say the forest model is automatically activated, it means that, of course, we will modify the Navier-Stokes equations, mainly using a volumetric sinc term, okay, and we will also modify the mixing length in the 𝗊𝗍 equation inside of the Navier-Stokes equation. Okay, so to illustrate this activation, you have here an image of the vertical mesh, okay, with the different cells. So if we take, for example, this cell, okay, or this one, so the roughness length is 0.05, okay, meters. So if we multiply by 20, we got the 𝗀𝗃𝗃𝗁 height, so it's 1 meter, and 1 is lower than 4 meter, which is the height of this cell. So the forest model is not activated. Now, if we take this cell, okay, so the roughness length is 0.5 meters. We multiply by 20, okay, now we have 10 meters, okay, of course, 10 is higher than 4, so here we activate the forest model. And of course, we reproduce this process for all the mesh. So now we can talk about this drag force term, okay. So you see here, this force is depending on the air density, the mean speed, and also on this CD parameter, okay. And this CD parameter is very interesting because it depends on the density of the forest. So we call it density of the forest. Actually, this is a internal property of the forest, like type of the trees, the real density of the trees inside of the forest. And it's also a kind of adjustable variable, okay, of the model. So you have here the main interface, okay, to configure this CD parameter, okay, so the density of the forest from low to high. Of course, you will act on the drag force term using these different variables. And this CD parameter also depends on the position of the cell in the forest, okay, so because we have less leaves in the top of the trees, of course, we simulate this effect by a reduction on the top 25% of the forest. So we have here the normalized CD parameter. So here you are inside of the forest, okay, and then when you are on the top 25% top of the trees, you see this reduction, okay, of the CD parameter. So of course, these different elements are interesting to present the calibration methodology. So the purpose here is to improve the simulation accuracy, okay, and the idea is to adapt the forest effect on the real site location, okay. Why? Because the default parameters are probably appropriate for 80% of the sites, but if you are working on specific forest, specific sites, you need to adapt these parameters. Okay, so the idea is quite simple. We just need to compare the wind profiles between meteorological data, okay, and the CFD computation using neutral conditions. Why? Because of course we want to remove the effect of the stability in this approach. So on one hand, on the right here, you need to launch CFD computation, okay, so with neutral conditions. So this is the class 2 in the software, and you can tune different parameters, okay. So of course I will explain the next slide, but you can act on the forest density, okay, or the CD parameter. You can also modify the height of the forest, the height of the trees, so you can modify the roughness length directly, or this ratio. So this is the ratio between the tree height and roughness length, which is by default the 20 value. And on the other hand, here on the left, you need to reproduce neutral conditions, okay, for the data. So in the past, we used to have this approach. We recommended to apply some filters on high wind speeds during some conditions, okay. But of course, we had a lot of debates. What is high wind speed? So is it 8 meters per second? Is it 10? Is it 12? So according to a lot of observations and different studies, we decided to simplify this methodology, okay. And we have this new approach. So if you are in moderately complex terrain, okay, if of course you are in forested area, so it means that the roughness length is higher than 0.3 meters, okay, you consider full year data, so at least 1 year, but of course if you have 3 or 4 years, you have more statistics, it will be better, okay, and standard profile, so it means log evolution, okay. So now here, this is the assumption we take to simulate the neutral conditions, okay, and this is based on a lot of observations, because of course when you are working in forested area, you have so mechanical turbulences, so that the effect of the thermal stability is reduced to become negligible, okay. And of course, here the idea is to compare the different wind profiles and select the best forest density or the best parameters here to get the best fit. Okay, so if you want to apply it in the software, the idea is to compare wind profiles between data and CFD computation, okay? So you can duplicate the site, modify the forest density parameter from low, normal, or high. And if necessary, you can modify the CFD advanced parameters. Okay, so here you have access to this value, so the ratio between the tree height and the roughness, so by default 20. Okay, And you have here access to the real values of the low, normal, and high forest density. So just to show you directly on the software. Okay, so when you import, so this is the site description. Okay, so you have here the simulation. So it means that you will describe, of course, the radius, the center of the site. And here you import the different maps. Okay, so you see here when you want to import a new roughness map, you have access to the forest density from low to high. Okay, so then you have the elements. Okay, you know that you can create wind turbines, mapping, mast locations. Okay, and in the CFD configuration panel, okay, you have here access to the ratio between the tree height and the roughness. Okay, and here in the advanced parameters, you have access here to the real values of the densities, forest densities. Okay, Aurélien, maybe you can illustrate on one example, just to be clear on the methodology.
Yeah, sure. Just one quick comment on what you said before.
Yeah.
Just to remember that before the setup of the forest, the tree height ratio and the CD was defined for all the projects, and now it's project specific, meaning that you can customize it for each of your project. So that's quite good news for the how to manipulate it. Just an illustration of how to calibrate a mast and to compare basically measurement on site and the simulated vertical wind profile using CFD. So on the blue, on the graph, the blue point represents the measurement, the vertical wind profile, and as you can see on the orange curve is showing the vertical wind profile using the high parameter for the CD factor. And we can see that for the lowest height, the wind profile are not matching. On the opposite, using normal density, the gray curve, we can see that we can notice the blue profile and the gray profile are matching much more. So we could say that that using the normal density would be more appropriate for this site. So moving on the study itself. So just a short introduction on the context and the location of the project. So we wanted to use different sites around the world to cover different kind of environment, different kind of trees, also different kind of stabilities and climatology. So 5 sites were selected, and using each site was equipped with two different medmasts with a common concurrent period and also concurrent height, in order to be able to make cross prediction between the two masts and in the objective to assess the performance of the model compared to the measurement. For each of those sites, we use the Roughness crawling land cover, public available, and at some point some manual correction have been made. And about the CFD computation meshing, only the default parameter has been used. So based on for each site, we have been we looked for the cross prediction as a main KPI to assess the performance of the software, the model. So as Leonard said, only a neutral condition have been investigated, and different setup of forest parameters. So you can see on the table the distance, a shorter recap of the distance between the masts. So you can see that we have some masts pretty close from each other, but on some site we have some distance. And you can see also some elevation. So the idea initially was also to use a flat terrain, but with forest area, in order to remove the effect of the terrain itself. But yeah, most of the time you have some semi complexity, so it's not 100% flat, and some effect of the terrain could also be involved in the model. And as you can see on the right column, so pretty high value of the roughness have been used for each of the sites. So how just a short slide on the result, on the global result for all the sites. So using for the two first sites, so yeah, just for you to understand how the results are illustrated. So on the table, you have the mean error, mean wind speed error on cross prediction between the two masts. On the left column, the result, the wind speed error is obtained with the default parameter, and on the second column, using the forest model calibration, meaning you are using a different forest density and tree height ratio. And on the third column, you can see the improvement, the reduction of the deviation of the cross prediction between the two masts. And on the right, you can see the parameters used, retained for the final model. So you can see that for the first two sites, the calibration of the forest has almost no impact on the cross prediction between the two masts. And using default parameters is showing the best results. On the opposite, you can see for the three other sites, you can see a slight improvement for the site 3 and 5, using a high forest density and a ratio of 40. So around 1% of improvement. And for the fourth site, much more improvement was found, more than 4%, using a tree ratio of 60 and a CD factor of 0.1. So it's we will come back later on this, but it was necessary for this site to use even higher density than the highest density available by default. So focusing on the site 3, so you can see the almost 7 kilometers between two masts, and yeah, heavier forest everywhere on the site. And 1 year of data, concurrent data, have been used for the analysis, and the elevation is quite, the terrain is quite flat, with gentle slope. So yeah, looking at the graph itself and the vertical wind profile, You can see here that using different kind of calibration, default parameter, calibration 1 and calibration 2 are affecting giving different vertical wind profile. And we can clearly see that for the yellow curve is matching better the observation of both masts actually. And for this calibration, the CD factor of 0.02 and the tree height ratio of 40 was used. So sometimes, yeah, the CD factor needs to be a bit adjusted to manually to match the observation and the mast measurement. So that was for each mast itself. And about the cross validation, meaning from one point to another, we can see interesting results here. That's, of course, we have an improvement using at top height, but also we have an improvement at lower height. But you can see, that for the calibration 2, you have a better match at low height, whereas at top height, the difference between the two calibration is less pronounced. So yeah, it's logical because it's the tree height is affecting more the low height rather than the top height. So that's something we can notice on this site.
Yeah, so just on that slide, the idea is to give some tips because, of course, if you want to tune the model, it can require some computation time. Okay, so on this site, we try to work on the prevailing sector only. Okay, to see if we can save time just working on one sector for the CFD. So here you see the prevailing sector is around 200 degrees. Okay, and if we apply just the forest calibration on the speed up factors now and not on the mean speeds, okay, you see that we have the same very similar conclusions. Okay, so the calibration 2 is more appropriate to simulate the vertical profile. Okay, so this is of course some tips to save time.
Now a quick focus on the more complex site, the fourth site, which was located in semi-complex terrain, but with really high trees and really dense forest. And same, we used two masts at 100-meter high with 1 year of concurrent data. So about the forest calibration at each mast, it was a bit tricky for this one because it's not always easy to choose which setup of parameters is the best. As you can see on the first mast on the left, the calibration 2 seems to be more appropriated for the mast 1, and on the other hand, on the mast 2, the calibration it's the opposite. The calibration 1 is matching the vertical profile. So we could say, okay, we need 2 calibration for each mast. It's a bit tricky because if the 3 species are the same, it's not kind of logic. So at this point, you can ask yourself which calibration to consider.
Yeah. So it was a very interesting question. So we investigated a bit further these points. Okay. And of course, the idea here is to show you some way to, so what we call the roughness patch, to improve the accuracy of the simulation and to correct the roughness maps, okay, from the public database. So if you have a look here on the roughness map, okay, from the Copernicus 100-meter resolution map, okay, we can see that we have similar conditions around the mast 2 and the mast 1. So it means that we have here huge forests around each mast. However, okay, when we compared with the shear analysis and the images, we saw that the other results were very different. Okay, so if we have a look here on the shear analysis, at the mast 1, we have huge values of the shear around 0.5, 0.7. So this is really representative of high forest area. And for the mast 2, so it's very different because we have values around 0.2, 0.1. Okay, and of course this is more standard values of shear without forest. Okay, so sorry. And if we have a look on the image from Google Earth, we see that there is some significant tree cutting area around the mast 2. Okay, so of course there is inconsistency between the map, the public map, and the site. Okay, because of course the map has been determined in 2019. Now we are in 2022-23. So of course, if you have some changes in the maps, you cannot see. So we decided to use what we call the roughness patch. So the roughness patch is just a modification of the map. Okay, so you can do it easily with the software. So you can create with a GIS tool like Global Mapper this TIFF file. Okay, and then in the software you can import this TIFF file. You can customize the roughness length. Okay, and here you can of course combine different maps. Okay, to correct. So this is what we see here. Okay, we have this new roughness area here. Okay, so if you want just to see in the software, so here in the simulation, okay, so instead of just one map, you can combine two roughness maps. Okay, and you see here, okay, so you have this green area, so this is a different site. Okay, but you have this roughness patch customized for this site. Okay, and now if we have a look of the forest calibration at the mast 2 without and with the patch. So without the patch, we had this calibration 2, which overestimates the forest effects. Okay, so now, of course, we remove the forest around the mast. So we reduce, okay, the forest effects for the calibration 2 and the calibration 1. Okay, and now, of course, it's difficult to conclude on which one is the best, but well, at least 1 and 2 give very similar results. Okay, for this calibration. And now, if we have a look on the cross validation, it's very interesting. So from the mast 1 to the mast 2, okay, so in orange here in dot line you have the data. In the blue you have the wind profile. So without any calibration, you just take default parameters. Okay, and now if we take the calibration 2, you have the yellow curve. And if you add this patch, okay, you modify mainly at 60 meters the vertical profile, but now we of course we match the data. Okay, so of course this is huge forest. Okay, the height of the trees is around 40 meters. Okay, and the mast is located inside of the mast 1 is inside of the forest, and the mast 2 is in the surroundings of the forest. So here the effect is huge, okay, because of course at 100 meters we move from 6.4 to 2.2, okay. There is a small effect at 100 meters, but of course if you do the average of all heights, the difference is very significant from 8% to 2%. Okay, so the idea is not to apply roughness patch on all your sites, okay, because of course you see the effect that the hub height is probably lower, but the idea is to propose and to give you some methodology if you want to go deeply into the details of this approach. Okay, so here goes the conclusions. Aurélien, maybe you can start for the conclusions on your side, and then I can take over.
Sure. So what we found from this study is that it's definitely there is definitely a need for the forest calibration in the heavy forested area. So sometimes it is not having a significant impact, but sometimes it is. So that's one point, and especially with when it's especially important when the tree height is really high, and also when the density of the forest is important. So special attention might be given for those sites. And if we want to, as Leonard said, if we want to go deeper on the vertical profile modeling, then it's interesting to have a look to the Roughness data, and it's important also to. That's why it's also important to go on site and check the environment and compare it to the data, to the input Roughness data used in the CFD model.
Thanks, Aurélien. Yeah, so just one tip, I showed you that of course you can simplify the methodology applying just on the prevailing sector, okay, of course the very directional wind roses, you will save time, and of course the one of the questions in the introduction was, are roughness databases accurate enough? Okay, because of course today there are a lot of roughness maps determined by lidars, by planes. Okay, so according to this study, okay, so the answer is yes, because actually the mean cross-validation error on these 5 sites is around 2%, so which is actually very good results. Okay, but of course here we saw that we need to be careful with these maps and eventually correct with the roughness patch or manually with the digitalization tool. Okay, so these projects, well, the results of the project have been published in one poster in Wind Europe in Bilbao in March. Okay, so you can see now it's available. So of course I would like to thank you all the team from EDF Renewables and especially Aurélien to be here with us today. And of course, if you have questions, don't hesitate, we have time for that now.
Okay, thank you, Edouard. Thank you, Aurélien.
So I have one question about, so if we consider the stability calibration and if we evaluated the KPI relating of course considering the stability, so this is a very interesting question. So for that step, okay, for the forest calibration, we need to of course to remove the effect of the stability. Okay, So this is what I said during the presentation. In most cases, so in that project and according to many other studies, when you are working on highly forested areas, okay, you have some mechanical turbulences due to the forest, so that the effect of the stability is reduced, okay? So considering 1 year, 1 full year, okay, is a good way to, of course, to simulate the natural conditions. Of course, if you have just 1 month or 2 months, I would say be careful because you have probably some effects of the stability. Now, if you are working on very complex terrain, so if you are working on mountains, I've just finished some studies in the Alps mountains. So you have so many influence of the orography, so that you don't have the orography is the factor that drives the wind flow, okay, and you have a very low effect of the forest. So this is why the methodology and the strategy is dedicated to moderately complex terrain. If you're working on mountains, okay, be sure that you have a good convergence, and be sure that, of course, you want to consider the stability. So one question, is it possible to use several forest maps to present different periods like measurements and operational periods? So yeah, the idea is to, so it's a good question. So we had some questions about, for example, what about winter and summer? Is it possible to, or is it relevant to consider different maps? And of course, so this is maybe a project for the future to investigate the effect of the leaves between winter and summer. So here we had many pines, so we didn't have these effects. But of course, yeah, if you have, you can of course easily change the roughness maps. Another question, how did you carry out the cross coloration for each sector or across all sectors? Did you filter the data beforehand? So yeah, it's also a good question. What about the sector? So for all that projects, the masts were located inside of the forest. So it was, well, easy for the analysis because we just consider the mean profile. If you have different sectors with very different conditions, okay, you can apply the calibration sector by sector. Okay, I'm currently working with one project where the mast is on the coastal side. From the west, the wind is strongly affected by the forest. From the east, we have the wind from the sea. So this is a typical case where you can calibrate from the land, the wind coming from the land with this forest calibration. And for the wind coming from the sea, you can of course use another strategy, probably more stability calibration. Okay, and you can of course improve, and we in this project we improve sector by sector the simulation accuracy. So I have another question about the effect of the roughness on the wind turbines. What is the maximum distance of? So this is also an interesting point. We generally consider that the effect of the forest is around 30 times multiplied by the height of the forest. Okay, so if you have trees around 10 meters, it's 300 meters. So let's say you have an impact between 300 meters and 600 meters maximum effect. Okay, so of course, if you have some doubts, the best way is to just to compare the vertical profile from the data and the simulation, and of course you will see clearly if you are matching the data. If it's not the case, okay, you can tune the model. So of course the idea. So one interesting question was how to determine the ratio. So of course the
Yes.
starting point is is the height of the trees, because this is something we know from the site. Okay, so with this project, so Aurélien, you had some estimation of the height of the trees. So the first parameter to adapt is the ratio. Okay, so if you know the roughness length and the ratio, of course you can deduce easily the real height of the forest. Okay, and then
yeah, and it will
and then the forest density, of course, is the adjustable parameter.
And do you think that adjusting also the minimum vertical resolution alongside with the tree ratio could affect this, could change this, you know?
Yeah, of course. So the minimum vertical resolution is 4 meters, okay, and this value is applied for the 10 first cells of the mesh. So it means that we have 40 meters with the best resolution, and then we have this effect of the increase of the cells. So yeah, it's a good question. Of course, if you increase this number of this first cell, maybe from 10 to 20, you can increase the accuracy. But of course, you will also increase the computation time. So it's always a compromise between accuracy and computation time. Yeah.
But if we put the vertical resolution to 2 meters instead of 4, we can do that to improve it, or we must stay at 4?
Well, we show that with 4 meters here, we have accuracy around 2%, which is very good results. So I'm not convinced that generally 25 the default parameters of 25 meters and 4 meters are totally adapted for the simulation in wind farms.
So we must more focus on the ratio, on the density, on the patch before running through the verticality of the cells.
Yeah, because you can also, you can bring some convergence issues when you decrease the size of the mesh. So working with 4 is maybe more robust. Yeah.
Okay.
So yeah, is it possible to use different CD values in different locations of the site on different density? So yeah, if you have very different conditions, you can divide, for example, your map in 4 maps for all different different sectors, different directions, and you can customize your CD value for each sector. So this is something that was not this was not the conditions of that project, but in my case, with the land and the sea, you have this kind of effect, and you need to customize really the roughness maps according to the site. Yeah, could be an interesting approach. Okay, Bertrand, I think.
Yeah, I'm looking what. When you input more than one roughness map in the project, they read from the top to bottom or bottom to top. I don't remember.
Yeah, it's a top to bottom. The last one is it is the same order between files, layers, and maps.
Okay, if we look over, we see the top to bottom.
Yeah.
So the larger one must be the bottom one.
Yeah. So you see in that example, the patch should be on the top, and you see clearly here the effect of the patch. If you don't see the patch on the roughness map, it means that it doesn't work. So are there similarities between sites 1 and 2 that can explain that the default parameters are good? Yeah, of course. So the calibration mainly depends on the height of the trees, because of course these public databases. Copernicus map underestimate generally the roughness lengths. So if the roughness length, and if the height of the trees is higher than 15 meters, we'll have, in all cases, an underestimation of the height of the trees, and of course you need to calibrate and at least increase the ratio between the height of the trees and the roughness. So the site with the highest improvement of the cross validation is of course one site with the highest height of the trees. It was 40 meters, so it's huge forest. Yeah.
Okay, so maybe we'll stop here. It's 1 hour. The replay will be available. The presentation will be sent to you, and the question and answer we do not yet answered will be also done in this email you will receive in a week or two. Okay, so thank you everyone for your participation. So we stay everyone in touch, and thank you Edouard again. Thank you Aurélien and EDF for your collaboration. So have a nice day everyone.
Thank you.
Thank you. Bye.
Bye bye.